Okay, so I'm going to postpone any introductory remarks for a moment. So let's start with Hoare triple. So this is one way of describing Hoare triple, right? So if we start from the precondition P, and we consider all the states that can be obtained from precondition P, then Q is a superset of those states that can be so obtained, right? That's one way of describing Hoare triple. Now we're going to do something to Hoare triple. Oh, we're going to take that up. We're going to move in this other symbol. And we're going to get rid of that one. And we're going to put a different notation there since we've changed his triple, right? So this is what I'm going to study in this talk. There's some prior art. I should mention this nice paper by De Vries and Kutavas, who study this notion using a different but equivalent definition. And you could have defined this in terms of dynamic logic in the 1970s. And you could have defined this 1 second after Hoare's logic just by going like that, like I just did, right? But the question is, I mean, why would you do this, right? I mean, why would you do this? Let me try to explain again. Let me try this again, okay? Let's start with Hoare's triple. What's that subset mean? That subset means over-approximation. What does over-approximation mean? Well, it means goodness in some sense, but it means there's the possibility of false positives, is what over-approximation means. So there's a false positive, true positive. Now, let's try to get inside the black instead of outside of it, right? That's what we're doing. Oh, come on. Let's move that over there. Let's move, what we've done by shifting that is we've gotten inside the black. So now, the net effect of this is that this different triple, it has no false positives in a sense. But guess it's under approximation, right? But guess what? You have no false positives, but it's opened the door now to false negatives, right? Okay, so now you might be like very unhappy with me. I mean, I'm evidently a bad person, and I've committed a sin against the church of thou shalt prove the absence of bugs, right? But I'm not going to repent, and I'm going to like try to argue that, no, I'm a good person, and I'm doing this in order to help people. And hopefully that will come out. So we're doing theory here to try to help people. And under approximation is a good way to do it. So why would I do this, right? So I was a theorist. I still am a theorist, apparently. I joined Facebook in 2013. And the tool, there's Cristiano and B and Dino and I covered up there. But the theory that was the result, the basis of the tool that we took into Facebook was from a POPL paper. This POPL paper was a typical verification paper based on over-approximation. So then I go into Facebook, and this has worked quite well. So there's been over 100,000 bugs fixed inside Facebook as a result of this tool. And there's more stats that we can quote to say it's worked pretty well, right? So you might think, so I should be happy about this, right? But actually, I mean, maybe as an engineer I'm happy, but as a scientist, I'm extremely irritated by the whole situation. And that's because the deployment of this tool is as a bug catcher. What it does is it tries to find bugs in whenever a code change is submitted to the Facebook code bases, it tries to see if this is a new potential bug. So it tries to catch regressions. It's not providing value to prove that none exist. Its value comes from when there's a failed proof, we use heuristics to try to say that there's a problem, and that's how we provide value. So this doesn't sit well with me, right? Like the compositional nature of the algorithms that came from the theory are responsible for why this can scale to large code. They're responsible for why it can be deployed in an incremental way, but the over-approximation has nothing to do with why the tool is successful. So that irritates me. So we've started making tools that are based on similar ideas, but that aim for under-approximation rather than over-approximation. And as I was thinking about this, the tools have principled architectures, just like ones based on compositional abstract interpretation, shall we call it, but they're not over-approximate. So I've been thinking to myself, there must be some missing theory to explain what's going on in these effective tools. And this talk isn't the full answer to it. This talk is one part of the answer. And I've gone back and simplified and simplified and simplified as much as possible to get to this point. And there will be further papers on this too. So that's how we get there. I'm sort of forced into this by becoming irritated by the theory not explaining the practice, which is successful. And so the way I'm going to set things up is something like Hoare's logic, but I'm going to have two kinds of post conditions. One for errors, one for OK normal termination. This is going to always be the under approximate triple rather than the over approximate triple. So the post Q under approximates the states that can be reached starting from the pre. Now, so with these error triples, why do you want these error triples? Well, we're reasoning about bugs is the reason. But let's consider an example. So there's the classic paper, Smashing the Stack for Fun and Profit, right? Which taught people how to exploit buffer overruns, is what this paper did, right? And so one of the beginning parts of teaching people how to exploit buffer overruns was this kind of buffer overrun, where if you happen to give it a string that's bigger than 16, then you're going to get a buffer overrun. So I might consider, well, suppose it's okay to use logic to talk about bugs instead of just running the code to talk about bugs. Then in this case, we would say that the achieves assertion, I talk about the post assertion as an achieves assertion, says if the length is bigger than 16, then we can get an error. So I'm going to be using error assertions like this. Now I'm going to give another example of where it's not an error assertion, where it's just a normal OK assertion in the post assertion. So here we are. If I start with Z is 11, and I execute this code, then I'm going to get to the conclusion. Then Z equals 42 under approximates the states that can be reached in this program, right? Well, no, actually no. You know what? The funny thing that I won't put people on the spot and ask for questions. Every single person I've shown this has gotten this wrong because we're not used to under approximate reasoning. Actually, it's not an under approximate conclusion there. Because I can find a state where Z is 42 and X is 1 and Y is 2 satisfies the post assertion, right? But you can't get to it starting from the pre. You see, you won't get into that if X is even because X is 1. So why is this? So everybody I've shown it guessed wrong, including myself perhaps. People are unwittingly using this rule of Hoare logic, which is as I go down a path, I can forget information or I can drop conjuncts. They're unwittingly using this information. And so it turns out for under approximate reasoning, you just can't do that. You've got to remember a lot of information as you go along a path in order to remain under approximate. And so this is in fact a correct under approximate conclusion there. I have to remember the information about those if conditions. So this rule of Hoare logic, dropping the conjuncts in the post, it's not true because the rule of consequence for under approximate reasoning is different than the rule of consequence for over approximate reasoning. And what we can do here is we can make the post smaller so that we have Q primed implies Q. We can shrink the post going forward. Whereas in over approximate reasoning, you can grow the post going forward. So that invalidates that proof rule on top. But what it does as well is it validates a different proof rule. It validates this proof rule where what I get to do is I can't drop conjuncts, but I can drop disjuncts going forward. Now, if you're a program analysis person, if you've been implementing program analysis, at this point you start to get interested and happy. And the reason is because what this is about ignoring paths, right? You know, this bad person ignoring paths, but no, it's going to be sound to do so, right? And here's a wonderful little experiment. That's my colleague Jules, who's implementing an analyzer for C++ lifetimes, which is based partly on the ideas that I'm talking about here. And he ran an experiment. he ran his analyzer on a code base with hundreds of thousands of lines. And he set two limits, the 20 disjunct limit and the 50 disjunct limit. So when the analyzer at a given state saw more than 20 disjuncts, it didn't add any more. When it saw, so he could have done that with 20, or he could have done it with 50. He ran the analyzer with 20, and he found that it found almost all of the issues that was found with 50, 97% of the issues. But it did so much faster, right? So now I'm thinking of maybe not going after all 50. Is it worth it to go after that 3%, right? It's a judgment call whether to go after that 3%, but also having this distinction gives the engineers a knob to turn. And engineers love to have knobs to turn to play with things practically. So here's something I could do. I could set the 20 disjunct limit and run really fast and catch the vast majority of the issues at code review time, or what we call diff time. So we need a fast turnaround with the programmers. Maybe I could run the 50 disjunct case overnight. So I get all the issues, but I get them at different times. And maybe I don't cost as much in the data center if I'm running the one quickly over and over again instead of running the one that takes a long time. So you see that far from being a bad person from considering that we might be able to ignore paths, we give the engineers something to play with in order to help the programmers earlier. So I'm translating that statement into being under approximate gives you leeway in helping programmers more. So there's an interesting duality that comes out here. So for correctness reasoning, you get to forget information as you go along a path. That's called abstraction, and that's what abstract interpretation is based on. But you have to remember all the paths. And having to remember all the paths is where the difficulty comes in doing it, right? On the other hand, for incorrectness reasoning, you must remember information as you go along a path, but you get to forget paths. So that's the hard part in incorrectness reasoning, remembering that information. But this, forgetting paths, gives you the leeway. So you see, one's not better than the other, they just have different room for maneuver. One has room for maneuver in one dimension, and the other has room for maneuver in a different dimension. In general, so I talked about what Jules was doing. He was just chopping paths, right? That's a very blunt thing to do. In general, what you would like is to interpret, this is non-determinism, to interpret join points in a program. What abstract interpretation tries to do is, in order to be more efficient, it tries to squish the disjuncts, right? But in order to be sound, it squishes disjuncts in a way that over-approximates disjunction. We merely need to squish the disjuncts in a way that under-approximates disjunction. So I give another example in the paper, which is not so blunt as just chopping. But having chopping at your disposal is a good thing. Here we go. Here's another example of this shrinking the post, which is very interesting. So there's symbolic bug catchers like Clee, Sage, Dart, based on symbolic execution for testing. One of the really interesting things they do is, as they go along a path, the symbolic execution can get confused. There's a number of reasons why it can get confused. One of the reasons is that you hit an expression for which theorem provers aren't too good at. An example of an expression for which theorem provers are not too good at is multiplication, right? Theorem provers are good at linear arithmetic. They're not good at nonlinear arithmetic. So what they do in these cases, when they get confused, instead of stopping, they drop to the concrete. Maybe not the entire concrete. They might partially concretize a symbolic state and then continue on. Well, that's very interesting. So that's where we see this z times z, right? What we can do here is we can shrink the state by, consider the case when z is 7, right? Then y is 49. I get a sound under approximate conclusion that y equals 49 and x equals 1. That's a sound under approximate conclusion got by concretizing the z part of the state as we were going. So what we obtain here, so I didn't design this logic with this in mind, but the pragmatic analyzer principle in these tools of concretizing symbolic values corresponds again to this principle of shrinking the post assertion as we go along a path. Okay. Now loops. So here's some rules for loops. I'm going to get past them pretty quickly because they're not the most interesting ones. These rules together amount to symbolic bounded model checking. Symbolic bounded model checking is sound for under approximation, but not for over approximation. So it's good that we have these rules, right? So from symbolic bounded model checking, for this program, clean star, I mean, I execute x gets x plus 1 as many times, several times, and then you exit. The achieves assertion says, oh, I could get x equals 0, or 1, or 2, or 3 as the conclusion, right? I can get that with symbolic bounded model checking, and I could prove that with those things on the previous slide. But there's an interesting thing that CBMC does, which is the tool of Daniel Kroning et al. It tries to discover assertions which let you jump over the loop without just boundedly unrolling, whilst staying under approximate. In this case, suppose I knew that x is bigger than 0 was a sound under approximate conclusion of the loop, then I could prove this bug, right? I do loop 1, then if x equals 2 million, then error, that I can reach that bug. I can prove it from this under approximate assertion. Now, I could do that with bounded model checking, but I'd have to unroll 2 million times. But then what if I gave it 4 million? Oh, now they'd have to unroll 4 million times. Or what if I had an n that was bigger than 0 and I didn't know what it was? If it was small, then you couldn't do it with bounded model checking. But we can get all those cases, and we can get them very succinctly, you see, if we have that assertion. So that's very good. Symbolic reasoning about bugs I think it can help us speed up the bug catchers. Okay, so there's a bit of in symbols what I just said about how we can get that bug if we have that information. But how are we going to get that post? How are we going to get that? Well, I'm going to need another proof rule for loops. And this other proof rule, I designed it based on this intuition. If I look at this triple, then what it means is for every state in the result is reachable from some state in the precondition. So if you think about executing backwards, every state in the result I can get back to the pre executing backwards. And now if I think about a loop, I can go over and over again backwards, and I'm going to get back to the pre. I might get elsewhere too, but I'm going to get at least by one path back to the pre. So this leads to a proof rule, whereas normally, you see there's an aspect of termination here. Normally when you reason about termination in over approximation, you use variance. A quantity has to go down going forward. So based on my explanation here, a quantity is going to go down, but going backward. So I designed the proof rule like this, where, so P of blank, the blank position is going to go down going backwards. You see from n plus 1 to n. And then this justifies this kind of post. And now, if I go back here, then I can obtain the post there via an instance of that inference rule where I'm selecting as my P of n, x equals n. So that's that x is going down in the backwards direction. If x is going up in the forwards direction, is the one you select here. So you see, you don't want to have loop invariants for reasoning about under approximation. Loop invariants are not good for reasoning about under approximation, but something like loop variants, but not the exact same thing, are very good for reasoning about under approximation and can give you more than the symbolic bounded model checking. So I have sort of a hope that under approximate tools are going to make use of techniques for discovering ranking functions and the like in order to give more succinct summaries for procedures and ways to find many more bugs more quickly. I have some hopes for that in the future. So, here's another final technical point I'm going to make. So suppose I've got a loop, and then I get an error inside the loop. So I can't use that previous proof rule. What's that? Oh, it's over time. Okay. Well, you'll have to trust me that I can prove that because I've got a completeness theorem. So in order to conclude then, what I'm hoping is that we get faster and smarter dynamic bug catchers. And I'm also hoping that testing and verification can come together on a more unified foundation. And I just wanted to end with this thing. So Dijkstra said this. right? And people have sometimes poo-pooed testing from the verification perspective. And thanks to the POPL referee for this comment. But I'm hoping in a few years we won't need to make this kind of comment. Okay, thank you.
Question. Oh, questions over there? Oh, no questions? Oh, okay, over there.
Okay, thank you for the great talk. So I was wondering about combinations of over-approximation and under-approximation reasoning. Did you search into that?
Oh yes, and in fact, the Facebook tools do that. First they go over, then they go under. It's hard to go straight under, but we're trying to make a theory about that as well. But the tools actually do combine the two. Yeah.
Yeah, there is a question from Slido. Is there a fundamental difference to under-approximating weakest preconditions?
Yes, under-approximating weakest preconditions is a great way to get an over-approximating triple. See, it's under-approximating in the forwards direction is very different. So yeah, it's extremely different. Yeah.
Okay.
So there seemed to be a connection between incorrectness triples and what would be called sort of total correctness triples, because you had your sort of loop variant type things. In correctness triples, you have partial and total variants for termination and not worrying about termination. Do you have the same duality over in incorrectness world?
It might be possible to make something like that, but I haven't looked at it.
Last question.
Okay, in all the examples you have shown in the talk, you are considering numerical properties.
Yes.
So when considering memory properties, you have to sometimes resolve which cell are going to be modified by some statements. And at that time, I guess under-approximation reasoning becomes a bit more difficult.
Oh, actually, it's funny you should ask that. I mean, I'm doing a paper with Azalea Rad, who's probably in the audience, and Derek Dreyer and Hai from MPI, as well as some of us from Facebook. We've got an incorrectness separation logic, which actually can't be obtained by just putting the two together. There are some trickinesses, and the first way to do that falls to pieces, but there's a way to do it. Yeah. And so it's quite interesting.
Okay, thank you. Okay, Peter. Yeah.